In 2011, a study by Serbian astronomer Milan Cirkovic looked at our place in the galaxy. He and his colleagues examined the galactic habitable zone. This is a specific region of the Milky Way where life like ours could plausibly exist. It turns out this zone is a very narrow ring. Our solar system sits comfortably within it, about 27,000 light years from the galactic center. If we were much closer, life would be impossible. The center of our galaxy is a violent place. It hosts a supermassive black hole, Sagittarius A, with a mass 4 million times that of our sun. The density of stars is immense. Supernovae, the explosive deaths of massive stars, are frequent. These explosions sterilize huge regions of space with lethal radiation. A planet too close to the center would be regularly scoured clean of any life. But if we were much farther out, life would also be unlikely. The outer regions of the galaxy are poor in heavy elements. Elements like carbon, oxygen, and iron are forged inside stars and scattered by supernovae. These are the building blocks of rocky planets and of life itself. In the galaxy's outer rim, there simply wasn't enough of this material to form planets like Earth. So we live in a cosmic sweet spot, a place that is not too hot, not too cold, not too violent, not too barren. This incredible fortune is just one piece of a much larger puzzle. The laws of physics themselves seem perfectly tuned for our existence. The strength of gravity, the mass of an electron, the energy of empty space. If any of these values were slightly different, the universe would be a sterile, empty void. This apparent fine-tuning has led some physicists to a strange and profound conclusion. Maybe our universe is not the only one. Maybe it's just one bubble in a vast churning cosmic foam of other universes, each with its own laws, its own constants, its own history. And we just happen to live in the one bubble where the conditions were right. The idea is staggering. But the evidence from various fields of physics keeps pointing in that direction. Here are 20 ways our universe might be just a small part of something much, much bigger. Number 20. We might be living inside a computer. A single cubic millimeter of space-time can hold about 10 raised to the power of 69 bits of information, a limit known as the Bekenstein bound. The visible universe contains roughly 10 raised to the power of 90 bits. Physicist James Gates Jr., working on string theory, discovered what looks like error-correcting codes embedded in the equations of supersymmetry. These are the same types of codes used to find and fix errors in computer data transmissions. The smallest possible unit of distance in the universe is the Planck length, about 1.6 x 10 raised to the power of 35 meters. Below this scale, our understanding of space breaks down. The idea that we live in a simulation isn't just science fiction. It's a serious philosophical and physical argument. In 2003, a philosopher at Oxford University named Nick Bostrom published a paper that laid out the logic. He argued that one of three propositions must be true. First, civilizations almost always go extinct before they develop the technology to run highly detailed simulations of their ancestors. Second, advanced civilizations for some reason lose all interest in running such simulations. Or third, we are almost certainly living in a computer simulation. The logic works like this. If a civilization reaches a point where it has immense computing power, it could run what are called ancestor simulations. These would be simulations of their own history, so detailed that the beings inside wouldn't know they were simulated. They would have consciousness, memories, and a sense of a real world. Now, if a civilization can run one such simulation, it can probably run thousands or millions. For every one base reality, there could then be countless simulated realities. If you do the math, the number of simulated consciousnesses would vastly outnumber the number of real ones. So, if you are a conscious being, the odds are overwhelmingly high that you are one of the simulated ones, not one of the originals. This connects to the cosmic foam idea. Each simulation could be its own universe, with slightly tweaked parameters. A simulator could run a batch of universes, changing the strength of gravity in one, the speed of light in another, just to see what happens. This would create a multiverse of digital bubbles. Our universe, with its finely tuned laws, might be the result of a simulation designed specifically to see how life evolves. The laws of physics we observe would be nothing more than the lines of code that govern the program. The Planck length could be the resolution of the simulation, the fundamental pixel size of our reality. The speed of light could be the processor speed limit of the computer running our universe. This is a strange thought. It suggests our reality is not the fundamental one. It's a copy, an experiment running on some cosmic hard drive. And the FOOM of other universes might just be other files in the same directory. Number 19 universes could sprout from black holes. The density of matter inside a black hole is thought to be infinite at a single point, the singularity. But quantum mechanics suggests infinity is not possible in the real world. A single stellar mass black hole, if it were to form a new universe, would create one with a mass energy equivalent to about 10 raised to the power of 57 protons. Our observable universe contains about 10 raised to the power of 80 protons. This suggests our parent black hole would need to be stupendously large. A theory called gravastars proposes that instead of a singularity, a black hole's core is a shell of exotic matter, preventing an infinite collapse. What happens inside a black hole? According to Einstein's general relativity, all the matter that falls in is crushed down to an infinitely dense point called a singularity. But this is where relativity clashes with quantum mechanics. Quantum theory, which governs the very small, doesn't like infinities. They usually signal that the theory is breaking down. So some physicists have proposed a radical alternative. What if the matter doesn't get crushed to nothing? What if instead it rebounds? This idea is part of a theory called cosmic natural selection, or fecund universes, proposed by physicist Lee Smolin in the early 1990s. He suggested that when matter collapses inside a black hole, it gets so dense that it triggers the birth of a new universe. This new universe expands out the other side of the singularity, not into our space-time, but into its own separate dimension. It's like the black hole is a seed, and a new universe is the tree that grows from it. Our own universe, in this view, was born from a black hole in a parent universe. And the black holes in our universe are right now giving birth to countless child universes. This creates a cosmic foam with a kind of evolutionary pressure. In this model, the physical constants of a child universe are slightly different from those of its parent. There are small random mutations. Now think about which universes will have the most offspring. It will be the universes that are best at making black holes. To make a lot of black holes, you need a lot of stars. And to make a lot of stars, you need physical constants that allow for the formation of galaxies, stable atoms, and vast clouds of gas. In other words, the universes that are good at making black holes also happen to be the universes that are good for creating life. Our universe is so finely tuned for life because it's a descendant of a long line of universes that were successful at reproducing. The sterile universes, the ones where the constants are wrong, simply don't make many black holes and die out. It's Darwin's theory of evolution applied to the entire cosmos. The foam is a family tree, and we live in one of its most successful branches. Number 18, time might not have a beginning. The second law of thermodynamics states that entropy, or disorder, always increases in a closed system. The early universe was incredibly orderly, a state of very low entropy. The observable universe has a temperature of 2.725 Kelvin due to the cosmic microwave background radiation, but this temperature is slowly decreasing as the universe expands. Sir Roger Penrose, who proposed this model, won the 2020 Nobel Prize in Physics for his work on black holes, which are a key component of his theory. We are used to the idea of the Big Bang as the ultimate beginning, a moment in time 13.8 billion years ago when everything started. But what if it wasn't a beginning? What if it was just a transition? This is the core of Roger Penrose's conformal cyclic cosmology, CCC. He suggests that our universe is just one in an infinite series of eons. Each eon starts with its own Big Bang and ends in a cold, dark, empty state. And that end becomes the Big Bang of the next eon. Here is how it works. Our universe is expanding at an accelerating rate. In the far, far future, trillions of years from now, it will be a desolate place. All the stars will have burned out. All the black holes will have evaporated through a process called Hawking radiation. The universe will be a thin, cold soup of stray photons and other elementary particles with no structure and no sense of scale. At this point, something strange happens. In a universe with only massless particles like photons, time and distance lose their meaning. The universe forgets how big it is. Mathematically, this infinitely large and empty future becomes equivalent to the infinitely small and dense point of a Big Bang singularity. The end of one universe seamlessly becomes the beginning of the next. This creates a chain of universes, not a foam of bubbles existing at the same time. But it's still a multiverse concept. The universe has been reborn an infinite number of times before our eon, and it will be reborn an infinite number of times after. Penrose even suggests there might be detectable remnants from the previous eon. He points to certain patterns in the cosmic microwave background, the leftover heat from our Big Bang. He claims these could be the faint traces of supermassive black hole collisions that happened in the universe before ours. These Hawking points, as he calls them, would be regions of slightly higher temperature in the microwave sky. While the evidence is still debated by cosmologists, it's a fascinating possibility. Our universe might not be an isolated event, but just one chapter in an infinitely long book. Number 17, there is a copy of you reading this somewhere else. The number of possible states for all the particles within our observable universe is enormous, but finite. It is estimated to be around 10 to the power of 10 raised to the power of 122. If the universe beyond what we can see is truly infinite, then every single one of these possible configurations must repeat. A physicist named Max Tegmark has calculated that your nearest identical copy, or doppelganger, is likely located about 10 to the power of 10 raised to the power of 28 meters away. That's a 1 followed by 28 zeros. This isn't about different laws of physics. This is a direct consequence of standard cosmology combined with quantum mechanics. Our observable universe, the part we can see, is about 93 billion light years across. This is the distance light has had time to travel to us since the Big Bang, but we have no reason to believe the universe just stops there. Most models of inflation suggest that the universe as a whole is vastly larger, perhaps infinitely large. Now, think about what's inside our observable patch. It's made of particles arranged in a certain way. Quantum mechanics tells us there's a finite number of ways you can arrange these particles. The number is staggeringly large, but it's not infinite. So if you have an infinite amount of space, but only a finite number of possible arrangements, then those arrangements must eventually repeat. It's like having an infinite deck of cards with only 52 different card types. Sooner or later, you're going to see the same card again. This means that far, far beyond the edge of our visible horizon, there is another region of space identical to ours. A region with a galaxy that looks just like the Milky Way, with a star that looks just like the sun, and a planet that looks just like Earth. On that planet, there is a person who is an exact atom for atom copy of you. They are living a life identical to yours up to this very moment. And there isn't just one. In an infinite universe, there are an infinite number of them. There are also regions that are almost identical, but with one tiny difference. A universe where you chose a different breakfast this morning. A universe where you pursued a different career. A universe where a key historical event turned out differently. Everything that can happen has happened and will happen an infinite number of times over. This isn't a foam of bubbles with different physics. It's a single, vast universe where our local reality is just one of an infinite number of repeating patches. Number 16, our universe could be a sheet of paper in a vast library. String theory requires at least 10 dimensions to be mathematically consistent, 9 of space and 1 of time. We only experience three spatial dimensions. A 2015 experiment at the Large Hadron Collider looked for evidence of extra dimensions by searching for micro black holes that would evaporate instantly, but found none. In some brain models, gravity is the only force that can leak between different brains, which could explain why gravity is so much weaker than the other fundamental forces. One of the leading candidates for a theory of everything is string theory, or its more modern version, M theory. In this view, the fundamental building blocks of reality are not point-like particles, but tiny vibrating strings of energy. Different vibrations of these strings give rise to all the different particles we see, like electrons and photons. But for the mathematics to work, string theory needs extra dimensions of space. You know, we live in a world with three spatial dimensions: length, width, height, and one of time. String theory says there are actually more, perhaps as many as 10 or 11 total dimensions. So where are these other dimensions? One idea is that they are curled up or compactified to a size so small we can't detect them. Another, more dramatic idea is the concept of brains. The word brain comes from membron. In this model, our entire three-dimensional universe is just a brain, a vast sheet floating in a higher dimensional space called the bulk. Think of our universe as a single page in a book. We can move anywhere on that page, but we can't perceive the other pages. But there could be other brains, other universes floating parallel to ours in this higher dimensional bulk. They might be just a millimeter away from us, but in a direction we can't point to or access. This would create a multiverse, a stack of parallel universes. It's possible for these brains to interact. If two brains were to collide, the energy of that collision could be immense, enough to trigger a Big Bang. Some theories suggest that our own Big Bang was caused by just such a collision. It's also possible for things to travel between the brains. While most particles and forces are stuck to our brain, gravity might be an exception. Some models predict that gravity can leak out of our brain and into the bulk. This could explain a long-standing mystery in physics. Why is gravity so much weaker than the other forces, like electromagnetism? The answer could be that most of gravity's strength is diluted across these extra dimensions. We only feel a tiny fraction of its true power. Number 15, there are more possible universes than atoms on Earth. String theory's equations have a vast number of possible solutions, not just one. It's estimated there could be around 10 raised to the power of 500 different ways to configure the extra dimensions and fields required by the theory. Each of these solutions would describe a universe with its own set of physical laws and constants. The number of atoms in the observable universe is estimated to be around 10 raised to the power of 80. So the number of possible string theory universes is unimaginably larger. The cosmological constant, which drives the accelerated expansion of our universe, has a value of about 10 raised to the power of 122 in Planck units. In theory, its value could be much, much larger. This is the concept of the string theory landscape. It emerged from the realization that string theory doesn't predict a single unique universe. Instead, it predicts a colossal number of possible universes. Think of it like a landscape with many valleys. Each valley represents a stable, possible universe with a certain set of physical laws. Our universe is just one of these valleys. There could be 10 raised to the power of 500 other valleys, each a different universe. Where do all these possibilities come from? They come from the different ways the extra dimensions required by string theory can be curled up. The geometry of these tiny hidden dimensions determines the fundamental constants of the universe that exists on top of them. The way they are twisted and folded dictates the strength of gravity, the mass of the electron, and the value of the cosmological constant. With so many ways to fold them, you get a huge number of possible outcomes. This landscape provides a potential explanation for the fine-tuning problem. Why is our universe so perfect for life? Well, if there are 10 raised to the power of 500 possible universes, it's not surprising that at least one of them, by pure chance, would have the right conditions. Most of the other valleys in the landscape would represent sterile universes, universes that collapse in an instant, or that are filled with only radiation, or that have no chemistry. We find ourselves in this particular valley because we couldn't exist in any of the others. This idea connects directly to the cosmic foam of eternal inflation. Inflation could be the mechanism that creates bubbles of all these different types. As the meta-universe expands, it pops off new bubble universes, and each one lands in a different valley of the string theory landscape, crystallizing with a different set of physical laws. The cosmic foam, then, is a physical manifestation of this abstract mathematical landscape. Number 14, the universe might be a two-dimensional projection. In 1997, theoretical physicist Juan Maldacena proposed the ADS-CFT correspondence, a mathematical conjecture that connects a theory of gravity in a certain kind of space-time anti-de Sitter space to a quantum field theory on its boundary. A 2017 study by physicists from the University of Waterloo and other institutions found substantial evidence for the holographic principle by studying irregularities in the cosmic microwave background. They showed that a simpler 2D holographic model fit the observational data as well as the standard, more complex 3D model. The information content of a black hole is proportional to its surface area, not its volume, which was a key insight leading to this idea. This is the holographic principle. It's one of the most bizarre and counterintuitive ideas in modern physics. It suggests that our three-dimensional reality might be an illusion, a projection like a hologram of information stored on a two-dimensional surface at the edge of the universe. Think of a security chip on a credit card. It's a flat 2D surface, but when light hits it correctly, it produces a 3D image. The holographic principle suggests the entire universe works this way. The idea came from studying black holes. Jacob Bekenstein and Stephen Hawking discovered that the amount of information a black hole can contain is not determined by its 3D volume, but by the 2D area of its event horizon, its surface of no return. This was a shock. It's like saying the amount of data you can store on a hard drive depends on the size of its casing, not the number of platters inside. It suggested that information, the fundamental stuff of reality, is two-dimensional. Physicists Gerard Hooft and Leonard Susskind extended this idea from black holes to the entire universe. They proposed that everything that happens inside a volume of space, including our own conscious experience, can be described by information encoded on the boundary of that space. If this is true, then our universe is like a hologram projected from a distant 2D surface. What does this have to do with the cosmic foam? It changes our concept of what a universe is. Perhaps the bubbles in the foam are not 3D spaces at all. Perhaps they are different 2D information surfaces, each projecting its own unique 3D reality. The space between the bubbles might not be space as we know it, but a realm where the rules of information storage are different. Collisions between bubbles could be seen as the merging or interaction of these 2D information sheets. This radical idea redefines the very nature of space and location, suggesting that our universe is less a physical place and more a complex data projection. Number 13, our existence itself points to other universes. The anthropic principle comes in two main flavors, the weak anthropic principle WAP and the strong anthropic principle SAP. WAP, first articulated by Brandon Carter in 1973, states that the observed values of physical constants are what they are, because if they were different, we wouldn't be here to observe them. SAP is more controversial, suggesting that the universe must have properties that allow life to develop within it at some stage. A key example is the triple alpha process by which carbon is created in stars. If the strong nuclear force were different by even a fraction of a percent, stars would produce almost no carbon, and life as we know it would be impossible. This is a philosophical argument, but one that carries a lot of weight. in physics. It's called the anthropic principle. It starts with a simple observation: the universe seems perfectly suited for our existence. If the physical constants were just a tiny bit different, we wouldn't be here. So, how do we explain this apparent fine-tuning? There are three main possibilities. The first is pure dumb luck. The universe just happened to have the right numbers, and that's that. Many scientists find this unsatisfying. The second is a designer, some supernatural entity, intentionally set the dials of the universe to the right values to allow for life. This is a matter of faith, not science. The third option is the multiverse. If there is a huge, possibly infinite number of universes and all of them have random physical constants, then it's no longer a surprise that we find ourselves in one that is hospitable to life. It's a selection effect. Imagine a firing squad of 1 million executioners and they all miss. So you could conclude that it was a 1 in a trillion miracle, or you could conclude that you are in a situation where there are 1 million different scenarios and you are simply experiencing the one in which you survive. We are the survivors. We can only exist in a universe that allows for our existence. All the other universes in the cosmic foam might be out there, but they are sterile and empty with no one inside them to wonder why. The fact that we are here asking these questions is itself a piece of evidence. It's like waking up on a tiny, lush island in the middle of a vast ocean. You might wonder how such a perfect island came to be. But if the ocean is actually filled with trillions of islands, most of them barren rocks, it's not so surprising that you happen to be on one of the few good ones. You couldn't be anywhere else. The cosmic foam provides the ocean of other islands needed to make our existence seem less like a miracle and more like an inevitability. Number 12, the laws of physics are balanced on a knife's edge. The cosmological constant, which governs the acceleration of the universe's expansion, is about 120 orders of magnitude smaller than theoretical predictions. If it were even slightly larger, the universe would have flown apart before galaxies could form. If the strong nuclear force were just 2% stronger, protons could not form from quarks, meaning no atoms. If it were 5% weaker, the universe would contain only hydrogen. The mass of the neutron is 1.001378 times the mass of the proton. If this ratio were slightly different, stars would either not ignite or would burn out too quickly for life to evolve. This is the problem of fine-tuning, the most concrete and numbers-based argument for a multiverse. It's not a philosophical point, it's a statement about the cold, hard data of physics. The numbers that govern our universe seem to be dialed in with incredible, baffling precision. Let's look at gravity. It's a very weak force. Compared to the electromagnetic force that holds atoms together, it's about 10 raised to the power of 36 times weaker. If gravity were just a little bit stronger, stars would burn hotter and faster. They would exhaust their fuel in millions of years, not billions. That's not enough time for complex life to evolve on any orbiting planets. If it were weaker, stars and galaxies might never have formed at all. The initial clouds of gas after the Big Bang would have just dissipated. Then there's the balance of matter and energy at the beginning of the universe. The total density of the universe was incredibly close to the critical density needed to result in a flat, long-lived universe like ours. If the density had been off by just 1 part in 10 raised to the power of 60, just 1 second after the Big Bang, the universe would have either collapsed back on itself almost immediately or expanded so fast that no structures could form. This level of precision is like aiming a gun at a 1 centimeter target from a distance of 13.8 billion light years and hitting it. How do you explain this? Again, you have the same options: luck, design, or a multiverse. A multiverse, specifically a cosmic foam of bubble universes, solves the problem naturally. If eternal inflation creates trillions upon trillions of bubbles, and each bubble has randomly determined physical constants, then you've essentially bought a huge number of lottery tickets. Most will be losers. They will correspond to dead universes, but with enough tickets, you are bound to get a winner eventually. Our universe is one of those winning tickets. The fine-tuning isn't a miracle. It's just a statistical outcome in a vast cosmic lottery. Number 11 giant structures in the universe are being pulled by something we can't see. In 2008, a team of astronomers led by Alexander Kishlinsky found that a large number of galaxy clusters spanning billions of light years are all moving in the same direction at a speed of about 2 million miles per hour. This motion, dubbed dark flow, is not explained by the expansion of the universe or the gravitational pull of any known structures within our observable horizon. The flow is directed towards a patch of sky between the constellations of Centaurus and Vela. Subsequent studies using data from the Planck satellite in 2013 have cast doubt on the original findings, and the existence of dark flow remains a highly controversial topic in cosmology. Our local group of galaxies is moving. That's not surprising. We are being pulled by the gravity of the Virgo cluster, which in turn is being pulled by the Great Attractor, a huge concentration of mass. This is all standard gravitational physics, but what if there was a motion that couldn't be explained by anything inside our visible universe? That's the claim of the dark flow. The study that first proposed this looked at the motion of about 700 galaxy clusters. It used the kinematic Sunyaev-Zeldovich effect, which measures the subtle temperature shifts in the cosmic microwave background caused by hot gas in the clusters as they move. The results suggested a coherent, large-scale flow of matter that extends out to at least 2.5 billion light-years. This flow seems to be pointing towards something outside our observable horizon. It's as if our section of the universe is on a giant conveyor belt, being pulled by an immense gravitational source that we cannot see because its light hasn't had time to reach us yet. What could cause such a pull? It would have to be something unimaginably massive. A super concentration of matter from before the inflationary period, or perhaps something even stranger. In the context of the cosmic foam, dark flow could be the gravitational tug of a neighboring universe. If another bubble universe were relatively close to ours in the higher dimensional space that separates them, its immense mass could exert a gravitational influence that leaks across the boundary. Or it could be the remnant of a pre-inflationary structure that is now far beyond our horizon, a hint that our universe is just one small uniform patch in a much larger, messier cosmos. While the evidence for dark flow is contested, if it were ever confirmed, it would be a powerful piece of observational evidence that there is indeed something massive and important lurking just beyond the edge of what we can see. Number 10. There is a giant cold spot in the sky. The cosmic microwave background CMB is the afterglow of the Big Bang, and it's remarkably uniform, with a temperature of 2.725 Kelvin everywhere. However, there are tiny fluctuations of about 1 part in 100,000. The CMB cold spot, discovered by the MAP satellite in 2004, is a region that is about 70 microkelvins colder than the average. It is huge, spanning about 1.8 billion light years across. One explanation is a supervoid, an enormous region of space with far fewer galaxies than average. A 2017 survey found a supervoid in that direction, but most cosmologists believe it is not large enough to explain the entire temperature drop. When we look at the sky with microwave telescopes, we see a baby picture of the universe. This is the cosmic microwave background, a faint glow of radiation left over from about 380,000 years after the Big Bang. This picture is incredibly smooth, which is strong evidence for the theory of cosmic inflation. But it's not perfectly smooth. There are tiny, hot and cold spots which represent the seeds of all the galaxies and clusters we see today. But one of these spots is not like the others. It's called the CMB cold spot. It's much larger and colder than standard cosmological models predict should be possible from random fluctuations. It's a a massive anomaly in our best map of the early universe. So what is it? One possibility is that it's just a statistical fluke. If you flip a coin enough times, you'll eventually get a long string of heads. The cold spot could be the cosmic equivalent of that. Another idea is that it's caused by a huge supervoid between us and the CMB. An empty region of space would have a subtle gravitational effect on the light passing through it, making it appear colder. But studies have shown the void in that direction isn't empty enough to account for the full effect. This leads to a much more exotic explanation. Laura Mersini-Houghton, a physicist at the University of North Carolina, has proposed that the cold spot is a bruise. It's the remnant of a collision between our infant universe and another bubble universe in the cosmic foam. In the very early moments of the Big Bang, our bubble universe might have bumped into another one. This collision would have sent a shockwave through our universe, a ripple in the fabric of space-time. This would have pushed energy out of that region, leaving behind a colder, less dense spot that we can still see today imprinted on the CMB. This theory makes a testable prediction. It suggests there should be similar, smaller spots in other parts of the sky from other, less direct collisions. If the cold spot really is a cosmic bruise, it would be the first direct observational evidence of another universe. Number 9, the rules of physics might not be the same everywhere. In 1998, a team of astronomers studying light from distant quasars found evidence that the fine structure constant alpha, which governs the strength of electromagnetism, might have been slightly smaller in the past. The data suggested a change of about 1 part in 100,000 over 6 billion years. There's a 2020 study from the University of New South Wales looking at a quasar 13 billion light years away, suggested that alpha might not just change over time, but also vary in different directions in space, creating a dipole effect. This research is still highly debated and requires confirmation from other studies. We assume the laws of physics are universal, the strength of gravity, the charge of an electron, the speed of light. We believe these are fixed constants, the same everywhere in the universe and for all of time. But what if they're not? What if they can change? A handful of controversial observations have suggested this might be the case. The fine structure constant, known as alpha, is a key number in physics. It determines the strength of the interaction between light and matter. Its value is about 1/137. If it were different, the universe would be a very different place. Atoms might not be stable, stars might not shine. Some astronomical observations have hinted that the value of alpha might have been slightly different billions of years ago. By analyzing the light from very distant quasars' light that has been traveling for billions of years after astronomers can measure what alpha was like in the distant past. The results are not conclusive, but some studies suggest a tiny variation. If the constants can change over time within our own universe, it's a small step to imagine they could be completely different in other universes. In the cosmic foam model, our bubble universe froze out from the inflationary sea with a particular set of constants. But other bubbles could have frozen out with different values. Our universe might have an alpha of 1/137, while a neighboring bubble might have one of 1/150, and another might have one of 1/120. Most of these universes would be sterile, but a huge variety of them would exist. This would mean that the laws of physics are not fundamental. They are more like local bylaws, specific to our own cosmic neighborhood. The true fundamental laws would be the ones that govern the foam itself, the meta laws that determine how bubbles are born and what range of physical constants they can have. Number 8, universes might evolve to be better at making life. Lee Smolin's theory of cosmic natural selection, proposed in 1992, suggests that universes that produce more black holes will have more offspring. The theory predicts that the fundamental parameters of our universe, like the masses of particles, should be tuned to maximize the production of black holes. While our universe is very good at making black holes, it is not yet clear if it is maximally good, which is a key test of the theory. The theory also provides a potential explanation for the arrow of time, as each bounce inside a black hole resets the cosmic clock and creates a new low entropy state. This idea takes the multiverse and adds a Darwinian twist. It's called cosmic natural selection. As mentioned before, physicist Lee Smolin proposed that new universes are born inside black holes. He then took this idea one step further. He suggested that whenever a new universe is born, its fundamental physical constants are slightly different from its parents. They mutate randomly by a small amount. Now, apply the principles of natural selection. Which universes will be most successful? The ones that have the most children. In this model, that means the universes that are best at producing black holes. To produce a lot of black holes, you need to produce a lot of massive stars. To do that, you need a universe with laws that allow for the formation of huge galaxies, vast clouds of gas and dust, and stable atoms like carbon and oxygen. These are the exact same conditions that are needed for the emergence of life. So, over many generations of universes, the ones that are more hospitable to life will also be the ones that are better at reproducing. There is a selection pressure that favors universes like ours. Our universe is so finely tuned for life not because of luck, but because it is the product of eons of cosmic evolution. It inherited its life-friendly properties from a long line of successful ancestors. This theory is elegant because it doesn't just say there are other universes, it provides a mechanism to explain why our universe has the specific properties it does. The cosmic foam is not just a random collection of bubbles, it's an ecosystem with universes competing, reproducing, and evolving over time. The most fit universes are the ones that flourish, and we just happen to live in one of them. Number 7, the Big Bang might not have been a beginning. According to quantum mechanics, empty space is not truly empty. It is filled with quantum foam, a sea of virtual particles that pop in and out of existence on incredibly short timescales. The uncertainty principle, formulated by Werner Heisenberg in 1927, states that you cannot simultaneously know both the precise position and momentum of a particle. This fundamental uncertainty applies to energy and time as well, allowing for the temporary borrowing of energy from the vacuum to create particles. The total energy of a flat universe like ours is thought to be exactly zero. The positive energy of matter and radiation is perfectly balanced by the negative energy of gravity. The standard picture of the Big Bang is that of a singularity, a point of infinite density and temperature from which space and time itself emerged. It was the beginning of everything, but what if there was no beginning? What if the universe has always existed in some form? This idea comes from thinking about where the universe came from. One common question is, what was there before the Big Bang? The traditional answer is that the question makes no sense because before is a concept of time, and time itself began at the Big Bang. But some physicists, like Alexander Vilenkin, have proposed a mechanism by which a universe can arise from nothing. This nothing is not absolute nothingness, but the empty, lawless state of a quantum vacuum. He describes it as a universe tunneling into existence. In quantum mechanics, a particle can tunnel through an energy barrier that it classically shouldn't be able to cross. Vilenkin's model suggests the entire universe did something similar, popping into existence from a state of zero size. If a universe can pop into existence from nothing once, why not many times? The quantum vacuum, the nothing that preceded our universe, could be a timeless, spaceless sea from which universes are constantly emerging. This sea would be the true foundation of reality, and our Big Bang was just one of countless such events. This creates a cosmic foam not in space, but bubbling out of a pre-cosmic state. There was no single moment of creation. Instead, there is a continuous, eternal process of creation with an infinite number of universes bubbling up and expanding. Our 13.8 billion-year-old universe would be just one of the latest to emerge from this timeless quantum potential. Number 6, empty space is the engine of creation. The energy of the vacuum, known as dark energy, has a tiny but positive value, measured to be about 10 raised to the power of 9 joules per cubic meter. Quantum field theory predicts a value for this energy that is about 10 raised to the power of 120 times larger than what we observe. This discrepancy is known as the cosmological constant problem and is one of the biggest unsolved mysteries in physics. During the inflationary period, just fractions of a second after the Big Bang, the vacuum energy was vastly higher, causing space to expand exponentially. It grew by a factor of at least 10 raised to the power of 26 and just 10 raised to the power of 32 seconds. Quantum mechanics tells us that empty space, the vacuum, is not empty at all. It's a roiling, seething soup of energy and virtual particles that flicker in and out of existence. This inherent energy of empty space is called vacuum energy. And according to Einstein's theory of relativity, energy has a gravitational effect. Positive energy, like that in matter, creates an attractive gravitational pull. But this vacuum energy works differently. It has a kind of negative pressure which creates a repulsive gravitational force. It pushes space apart. We see this effect today. We call it dark energy. It's the mysterious force that is causing the expansion of our universe to accelerate. The dark energy we observe now is very weak, but it's there. The theory of cosmic inflation proposes that in the first tiny fraction of a second after the Big Bang, the vacuum energy was immensely powerful. This created a colossal repulsive force that blew the universe up from a subatomic size to something larger than a grapefruit in an instant. Now, combine this with the idea of a quantum foam. The vacuum is not a smooth, calm sea. It's a chaotic place with constant quantum fluctuations. This means the amount of vacuum energy can fluctuate from place to place. In most of space, the vacuum energy might be in a low energy state like the one we are in now. But in some random patch, a quantum fluctuation could kick it into a very high energy state, like the one that powered inflation. This patch would then begin to expand at an incredible rate, blowing up into a new bubble universe. The vacuum itself becomes the engine of creation. It's a perpetual motion machine that churns out new universes. Our universe is just one tiny piece of this vast, inflating metaverse, a place where the fundamental state of reality is an endlessly expanding, energy-filled vacuum that is constantly spawning new cosmic bubbles. Number 5, a runaway force is pushing everything apart. The discovery of the accelerating expansion of the universe was made in 1998 by 2 independent teams of astronomers and resulted in the 2011 Nobel Prize in Physics. The force driving this expansion, dubbed dark energy, is thought to make up about 68% of the total energy density of the universe. Dark matter makes up about 27%, and normal matter, everything we can see, is less than 5%. If dark energy is a phantom energy whose density increases over time, the universe could end in a big rip, where everything from galaxies to atoms is torn apart. We live in an expanding universe. For most of the 20th century, cosmologists thought this expansion was slowing down due to the pull of gravity. But in the late 1990s, observations of distant supernovae revealed a stunning surprise. The expansion is speeding up. Something is pushing the universe apart, and the push is getting stronger as the universe gets bigger. This something is what we call dark energy. We don't know what dark energy is, but the leading candidate is that it's the energy of the vacuum itself, the cosmological constant. In the cosmic foam model, this dark energy plays a crucial role. The space between the bubble universes is thought to be a region still in a state of rapid inflation, driven by a very powerful form of dark energy. This interuniversal space, sometimes called the bulk or the metaverse, is constantly expanding at a furious rate. It is this expansion that creates the room for new bubble universes to form and grow. Think of it like a pot of boiling water. The water itself is the inflating bulk. The bubbles of steam that form and rise are the new universes. The heat source driving the boiling is the dark energy of the bulk. Our universe is one of these bubbles. Inside our bubble, the dark energy has settled to a very low value, allowing structures like galaxies to form. But outside our bubble, in the space between universes, the energy is high and the expansion is ferocious. This runaway force is what makes the multiverse a foam. It's the repulsive energy that keeps the bubbles separate and drives the endless creation of new ones. Without dark energy, the multiverse might collapse. With it, the multiverse is an eternal, ever-growing structure, a cosmic froth that expands forever. Number 4, infinity guarantees a multiverse. In an infinite universe, any event with a non-zero probability must occur, and it must occur an infinite number of times. The mathematical concept of a Poincare recurrence time suggests that in a finite system, the system will eventually return to a state arbitrarily close to its initial state. For our universe, this time is astronomically large, far longer than the current age of the universe, but it's not infinite. However, in a truly infinite spatial universe, there is no recurrence. Instead, all possible states exist simultaneously in different locations. This is a purely logical argument based on the nature of infinity itself. Most cosmological models, especially those involving inflation, suggest that the universe is spatially infinite. It goes on forever in all directions. If this is true, the consequences are mind-boggling. An infinite space has to be filled with something. It's filled with matter and energy, governed by the laws of quantum mechanics. Quantum mechanics is all about probabilities. There is a certain probability for any given arrangement of particles. Now, consider a volume of space the size of our observable universe. There is a finite, though unimaginably large, number of ways that particles can be arranged within that volume. If the universe is infinite, then there is an infinite amount of cosmic real estate. So every single possible arrangement of particles must exist somewhere out there. Not just once, but an infinite number of times. This creates a level I multiverse, as categorized by physicist Max Tegmark. It's not a foam of separate bubbles with different laws of physics. It's one single gigantic universe. But within this infinite expanse, our entire observable history is just one bubble of reality. Infinitely far away, there is another bubble identical to ours, and another, and another. There are also bubbles that differ by just one quantum event. A universe where a single particle zigged instead of zagged 13 billion years ago, leading to a cosmos completely different from our own. A universe with no Milky Way, a universe where Earth never formed, a universe where the dinosaurs never went extinct. If it is physically possible, it is happening somewhere. Infinity is the ultimate creator. It doesn't allow for possibilities, it demands them. In this view, our universe is not unique. It's just our address in an infinite cosmos. Number 3, the early universe was a chaotic mess. Chaotic inflation was proposed by André Linde in 1983 as a refinement of Alan Guth's original inflation theory. In Linde's model, inflation can start from very messy, chaotic initial conditions. It doesn't require a specific, highly ordered starting state. The scalar field that drives inflation, the inflaton, could have had different random values in different regions of the early universe. The regions where the field's value was high enough would start to inflate, becoming their own universes. The Planck satellite, which mapped the cosmic microwave background with high precision, found that the universe is extremely flat, with a curvature value very close to 0 less than 0.4% margin of error, which is a key prediction of inflationary theory. The first models of cosmic inflation were a bit like balancing a pencil on its tip. They required the universe to start in a very specific high-energy state called a false vacuum. It was an unstable state, and when it decayed, it released a huge amount of energy that drove the exponential expansion. But this raised a question: why did the universe start in this special unstable state to begin with? Then came Andre Linde's idea of chaotic inflation. He proposed that the very early universe was not a neat, orderly place. It was a chaotic mess. The field that drives inflation, the inflaton field, had random different values all over the place. Think of it like a landscape with hills and valleys. In some places, the value of the field was low a valley. In other places, it was high a hill. Lind showed that in any region where the field's value happened to be high enough, inflation would automatically start. That region would begin to expand at an incredible rate, smoothing itself out and becoming a huge, flat, uniform patch. A new universe. This makes the birth of a universe like ours much more likely. It doesn't need special starting conditions. It just needs a chaotic field. And because the field is random, there will be countless places where inflation can start. Each of these inflating patches becomes a bubble in the cosmic foam. Some patches might have a slightly different field value, leading to a universe with slightly different properties. Our universe is just one of these patches, a region where the inflaton field happened to have the right value to create the universe we see today. The chaos of the beginning didn't lead to one outcome, but to an infinite number of them. Number 2, our universe is a bubble that formed in a phase transition. In physics, a phase transition is a change in a state of matter, like water freezing into ice. The inflationary model proposes that the early universe underwent a similar phase transition. It changed from an unstable high-energy false vacuum state to a stable low-energy true vacuum state, the state we are in now. The energy released during this transition powered the Big Bang. The process of bubble formation is called nucleation. In this model, our universe is a bubble of true vacuum that nucleated within a larger region of false vacuum. The walls of this bubble would have expanded at nearly the speed of light. This is the original mechanism proposed for how a bubble universe could form. It's an idea borrowed from the physics of everyday materials. Think about boiling water. When water reaches 100 degrees Celsius, it doesn't all turn to steam instantly. Instead, little bubbles of steam start to form at random points. These bubbles then grow and expand until all the water has changed phase from liquid to gas. The theory of inflation suggests the early universe did something similar. The metaverse, the space between the bubbles, exists in a high-energy state called a false vacuum. This state is unstable, like supercooled water that is liquid below its freezing point. It wants to decay to a lower energy state, the true vacuum, which is the state of our current universe. But this decay doesn't happen everywhere at once. Due to random quantum fluctuations, at some point in the false vacuum, a tiny bubble of true vacuum will spontaneously form. This is called bubble nucleation. This bubble of true vacuum is our universe. Once formed, it would expand outwards at nearly the speed of light, converting the false vacuum into true vacuum as it goes. The energy difference between the false vacuum and the true vacuum is released in the process, and this energy dump is what we perceive as the hot, dense Big Bang. It fills our new bubble universe with matter and radiation. Meanwhile, outside the bubble, the false vacuum is still there. And it's still inflating, and at other points in that vast inflating sea, other bubbles are nucleating. Each one is a new Big Bang, a new universe. The cosmic foam is a sea of false vacuum undergoing a continuous phase transition, with our universe being just one of the resulting bubbles. Number 1. The process that made our universe never truly stopped. Eternal inflation, the theory that underpins the modern cosmic foam idea, was developed primarily by physicists Andre Linde and Alexander Vilenkin in the 1980s. The theory is a natural outcome of most inflationary models. The key insight is that the exponential expansion of the false vacuum between bubbles is much faster than the rate at which new bubbles form and grow. This means that even though new universes are constantly being created, the volume of the parent metaverse grows so fast that it never runs out of space. It is an infinite, self-reproducing engine. If this theory is correct, the Big Bang was not a one-time event, it's a process that is still happening all the time in other parts of the multiverse. This is the core idea, the engine that drives the entire cosmic foam concept. It's called eternal inflation. Alan Gutht's original theory of inflation solved many problems in cosmology, but it had an ending. Inflation happened, and then it stopped everywhere, leading to our one universe. But later work, particularly by Andre Linde, showed that this might not be right. In most models, once inflation starts, it's very hard to stop it completely. Here's why. Inflation is driven by a high-energy false vacuum. This false vacuum decays into a low-energy true vacuum, creating a bubble universe. But the decay is a quantum process. It's probabilistic. It happens at some points, but not at others. So you have a vast ocean of false vacuum that is expanding at an exponential rate. At random points within this ocean, little bubbles of true vacuum, new universes pop into existence. But the space between these bubbles, the false vacuum ocean itself, is expanding so incredibly fast that it grows much more rapidly than it is eaten up by the new bubbles. The result is that the total volume of the false vacuum is always increasing. This means that inflation never ends on a global scale. It's an eternal, ongoing process. Our universe is just one bubble that formed in this eternally inflating metaverse. After our bubble formed, the space around it continued to inflate, creating more and more room for other bubbles to form. And it's still happening right now. Far beyond what we can see, new universes are being born. The process that created our Big Bang is not a historical event. It is a fundamental law of the cosmos that is in continuous operation. The cosmic foam is not a static collection of universes. It's a dynamic, growing, self-reproducing system that has been making universes forever and will continue to do so for eternity. This is the ultimate picture of the multiverse, a timeless, infinite foam where our entire cosmos is just one fleeting, momentary bubble.